Good afternoon. My name is Anna Godfrey.
And I'm Katie McFerrin.
We're going to present an investigation into shoaling changes pre and post deepening to improve dredging efficiency, and it's a case study at Savannah Harbor.
And also on this team are Doctors Rachel Bain and Michael Hartman.
So we'll begin with the introduction. A little bit of background is the Savannah Harbor is a deep draft federal navigation channel with depths of up to 55 feet. And the sediment within the channel is mostly fines with a high concentration of silt in the upper harbor and sand closer to the ocean inlet. We're focusing in this report on the inner harbor. Is the entrance channel was lengthened during the deepening, which is known as the Savannah Harbor Expansion Project, also known as SHEP. And there was not enough pre-SHEP survey data for a proper analysis. And the inner harbor was deepened from 42 feet to 47 feet authorized depth between 2020 and 2022. And this is a diagram when we refer to the lower harbor is the reaches from the inlet up around this curve, and then we have a middle harbor and then the upper harbor. And we're curious if shoaling increased post deepening. There's a widely held assumption that deepening a harbor will lead to increased shoaling, and this is often the case. Is this figure from Rosati in 2005 shows for St. Mary's Entrance Channel in Florida. You can estimate the dredging rate from the linear trend lines on the pre and post deepening data, and this example shows a significant increase in dredging rates post deepening. So recent studies show that deepening a harbor does not necessarily lead to increased shoaling rates throughout the entire harbor. Historically, deepening Savannah Harbor has pushed the shoaling upstream. And if you look at these shoaling rates for the entire harbor, which are marked in green on the graph on the left side, over previous deepenings, it appears that there's an overall increase. But if you break it down, you can see the decreasing rate of shoaling in the lower harbor, which is orange, and an increase in shoaling in the upper harbor, which is purple. And these change in rates suggest that there is, well, excuse me. This suggests that there's not much change in the overall shoaling, but in where it's shoaling. Generally, the question is how much will shoaling increase if we deepen rather than will it increase, and if so, where? And why does this matter? Savannah Harbor is a major deep water port in the South Atlantic coast, and it provides over 50,000 or 500,000 jobs, $33 billion in income, and $2 billion in taxes to both Georgia and South Carolina. And is listed as one of the top 10 harbors with the highest levels of historic shoaling in the Dredging Principles of Delivery memo from headquarters in 2021. And it requires approximately 5 million cubic yards per year of sediment to be removed annually for maintenance. So our goals are to improve dredging efficiency, to reduce the operation and maintenance costs, and beneficially reuse 70% of the dredge sediment by 2030. And this means that we need an estimation of increased dredging maintenance volumes in dredging cycle for the deepened channel. Lots of studies have been done on the Savannah Harbor. We looked at these historic reports, the historic dredging volumes provided by the district, hydrographic surveys from eHydro, the USGS monitoring gauge data and historic sediment data.
All right, so to jump right into the data, this is some example flow velocity data from Savannah Harbor. We have a gauge in the upper harbor, the middle harbor, and the lower harbor. The upper harbor gauge is located at the Houlihan Bridge. The middle harbor gauge is located at the USACE dock, and the lower harbor gauge is located at Fort Pulaski, down towards the inlet. So from this data, we found that the highest velocities are found in the lower harbor near the entrance, and that ebb tidal velocities are greater than flood tidal velocities. So we have discharge, flow velocities, and water levels for the entire harbor for the period 2010 to 2024. Unfortunately, there's no time series of salinity data in the lower harbor, so a time series analysis of salinity was not possible. And we'll touch on this again later. For the sediment data, there's been historic sediment data collection and grain size analysis done. The upper and middle harbor tend to have really high silt and clay contents, and this tends to remain suspended as a fluid mud or a low density shoal. This fluid mud layer may have been pushed upstream by the deepening, and we will come back to that later. The lower harbor is primarily sandy, and a lot of that sand is imported by the flood tidal currents. So to get into the analyses, the shoaling analysis was conducted using the Core Shoaling Analysis Tool, or CSAT. CSAT is a hindcast algorithm that calculates shoaling rates and volumes from historical hydrographic channel surveys, which we sourced from eHydro. It uses these shoaling rates to then predict future dredging volumes, and the shoaling rate grids can be used to identify shoaling hotspots. So if you see in this figure here, this red area is a shoaling rate hotspot. So in this study, we calculated shoaling rates for each of the National Channel Framework reaches in the inner harbor for the period before the deepening, pre-SHEP, and post-SHEP, or post-deepening. And I've included the link if anyone's curious about CSAT. So here's some example CSAT results from the lower harbor, marked by the star in this map. This is reach 5. So in panel A on the upper left, you're seeing the shoaling rates in this reach before the deepening, where blue is low or scouring, and then yellow is very high shoaling. And then that's in feet per year. In panel B, this is the shoaling rate in the same reach after the deepening. And so we can calculate the average shoaling rate in the reach before the deepening was 2.0 feet per year, increased to 2.1 feet per year after the deepening. In panel C, we're seeing just the change in that shoaling rate post-deepening, where blue is lower values of shoaling rates in each grid cell, and then red is really high shoaling rates. You can see these little hotspots right here. And finally, this lower right panel, panel D, is the change in behavior of each grid cell. Did it exhibit scouring behavior before the deepening and stayed scouring? Did it change from scouring to shoaling? Was it shoaling before and it's still shoaling after? Or was it shoaling before and now it's scouring after the deepening? And in this example, it was largely shoaling before and it's still shoaling. So this is an example of reach 12 in the middle harbor. So same figures, this is the shoaling rate before the deepening and after the deepening, and you can see a major change in the average shoaling rate for this reach, kind of echoed by this figure, which is mostly blue, so the shoaling rate decreased. And then the change in shoaling rate behavior shows that it's largely still shoaling, but there are areas that have changed to scouring. And the working theory for the cause of the scouring, especially near the center of the reach, is the ships tracking through the fluid mud and the other sediments and kind of pushing them to the edges of the channel. And finally, this is an example from the upper harbor. This is reach 15, marked here by the star. It's adjacent to the port and the Kings Island turning basin. Again, we have shoaling rates before the deepening and then after the deepening, with a significant increase in the average shoaling rate for this reach. Again, echoed by all the red in this lower left figure. And then we can see that the reach was shoaling and it's largely still shoaling, except for this purple area right here, which is again where the harbor and the Kings Island turning basin are located. So to break this down for every reach, what I did was I took the outputs from CSAT, which tell you the average shoaling rate in each grid cell for the time period that you ran CSAT, so pre and post deepening. And then I just made box and whisker plots. So for example, this black is pre-SHEP, so pre-deepening for reach 5, and then blue is post-SHEP, post-deepening for reach 5. And did that for every single reach that we looked at. So lower, middle, upper harbor. So what we find here is that the variability or the range of shoaling rates increases as you move upstream, especially after the deepening. This is true in reaches 5, 8, 10 through 12, 15, and 16. Also, the median or 50th percentile shoaling rate increased after the deepening in reaches 8, 15, and 16. And then what we see is a lot of the data, especially post-deepening, is positively skewed, which means that there are more extreme values on the higher end in this figure. Because these are oriented vertically, that's the upper end. So in reaches 5, 6, 8 through 16, and 25, we see this positive skew. So this means we're seeing a lot more of the extreme high shoaling rates than extreme low shoaling rates. However, I have to point this out again, is that we have 10 years of pre-deepening data and only 2 years of post-deepening data. So keep that in mind.
So we're looking at the historic dredging volumes. We have 14 years of dredging data in this graph. Notice there's a spike here at station 100. That's where the Kings Island turning basin is. And it requires dredging twice a year for maintenance. And you can notice that the higher volumes are located in the upper harbor reaches. Again, with the Kings Island turning basin, it acts as a sediment trap. It's very wide and it's deeper than the harbor channel at 55 feet. You can see where there's a decrease in volumes post-dredging in the lower and middle harbor. And then that indicates a relationship with decreased shoaling volumes in those areas. And again, we're looking at the historic dredging volumes, and you can see the quantities where it's pre-SHEP in the upper harbor. We're looking at 69% of the total quantity dredged per year versus post-deepening where it has jumped up to 87%.
So to plot those historic dredging volumes in a cumulative fashion, so on this graph we have fiscal year on the x-axis and then the cumulative dredging volume in millions of cubic yards. So these blue data points are pre-SHEP, so pre-deepening. The green are during the deepening. I just want to point out this is maintenance dredging volumes only. This does not include the new work. And then post-SHEP is here in red. So when you fit a linear trend line through these, again, you can start to estimate the dredging rates required in Savannah Harbor. So the slope of this line pre-deepening is 4.87 million cubic yards per year as an estimate. And then after the deepening, that increases to 4.99 million cubic yards per year, which represents a 2.45% increase in this estimated rate after the deepening. If we compare that to the figure we showed you earlier at St. Mary's Entrance, Florida, where they had pre-deepening deepening data and then post-deepening data. This was a 250% increase in the estimated dredging rate in this location. And there are many other examples of channels where there are significantly large increases similar to this one. So it appears that so far we're not seeing a huge increase in required dredging in Savannah Harbor. Again, with the caveat that we only have 2 years of data post-deepening, and that Savannah Harbor very well could be coming to a new hydrodynamic and geomorphologic equilibrium post-deepening, and that may not be finished yet. So it could still be settling out, and this behavior could change in the future. It requires further study. So in conclusion, we're finding that the dredging rates have only increased 2.45% post-deepening, but there's been major increases in the required dredging volumes in the upper harbor specifically, and less in the lower and middle harbor. The overall shoaling rates also have not increased significantly, but the shoaling patterns within Savannah Harbor have changed, with more shoaling occurring in the upper harbor and again less in the lower and middle harbor. So the specific processes driving these smaller scale changes are not yet well understood in Savannah Harbor, but again, it could still be coming to some kind of new equilibrium, and so we might see changes in the future to these trends. So potential future work includes studying the salinity intrusion post-deepening and the effects that has on the clay flocculation and settling, how that affects the fluid mud within the harbor. We would like to see some more data collection post-deepening, because again, we only have 2 years of post-deepening data as opposed to 10 years of pre-deepening data. And again, the entrance channel, as Anna mentioned, had been lengthened, so there was not very much pre-deepening survey data in order to do that analysis properly. And finally, it's been well studied the negative effects of ship wakes on channel erosion and nearby marsh and tidal flat erosion. That erosion can contribute sediment to the channel in the form of shoaling. And with deepening the channel, you can get larger ships into the channel, have larger wakes, and so the effects of ship wakes on the sedimentation patterns post-deepening are not understood at this point. And with that, we have some references, and then we'd be happy to take any questions.